If you're looking to be able to think critically about large language models, comparing them and understanding why they work the way they do and how this affects you and your work, then this course is for you. Join me to take a look at how we ended up where we are today with large language models, including looking at models such as BERT, GPT-3 and GPT-4, and Llama 2. Recently, GPT-4 and ChatGPT have become popular buzzwords. They're both large language models and are basically a type of AI that can understand and produce human like text. They can be used to do things like answer questions or generate content, summarize text, explain things, and generate dialogue. And we see large language models used in everyday tools like chatbots and virtual assistants and language translators. But things kicked off in natural language processing long before we had GPT and ChatGPT. In 2017, a type of AI model architecture called transformers was proposed by a team of researchers at Google in a paper called Attention is All You Need. All large language models use components of transformers as part of their architecture. So, how do large language models work? Well, we can interact with them with plain English text, often called a prompt, and the large language model will respond with text known as the completion or the output. Now, sometimes you won't get the output you expect, so you can change the prompt and you might get another and hopefully better answer. Now, let me illustrate working with a large language model with a simple example. So, you're trying to figure out which book to read your 6-year-old son. So, this is the children's book, The Adventures of Pinocchio. Now, you don't know whether he'd like it, so you take the first three chapters because you don't want to spoil the whole story and ask a language model to summarize it. And then, based on this summary, he can decide if this book sounds interesting. So, let me go ahead and grab the first three chapters. I'm going to copy that. And let's head over to a large language model and let's ask the large language model to summarize the first three chapters. So I'm now in OpenAI's playground. OpenAI are a large language model provider, and I'm going to use one of their best known language models called GPT-4 to summarize these first three chapters. So I provided as input summarize the following text in 5 sentences, and I'm going to paste the first three chapters. I'm going to head over to submit, and let's see the response back from the large language model. The large language model GPT-4 does a terrific job of summarizing the first three chapters. It starts off with carpenter Maestro Cherry finds a piece of wood that reacts when he prepares to carve it into a table leg, emitting a voice that seems to beseech him not to hit so hard. He eventually dismisses this, attributing it to his imagination playing tricks on him. Later, Geppetto, a friend of Maestro Cherry, arrives, and so on. And you can see that that's starting to look like a really good summary of the first three chapters. All right, so we've looked at what large language models are and that you can interact with them by providing a prompt as input and that they're trained on large amounts of data, which is why they return intelligent sounding text. Now go ahead and try out GPT-4 in the OpenAI playground and ask it some questions or ask it to explain something and see how good it is. We've seen an example of a large language model at work and the results are pretty impressive. But how do you go about training a large language model? And that's what we're going to look at in this video. Initially, the language model has random weights, and at this point, the model has no knowledge of language. Now, if you were to prompt it, it would just return gibberish. But if you train the model and passing it a large corpus of data, it adjusts these weights as part of the training process. And this pre training stage is very resource heavy, so you need lots of data, and this includes a variety of different types of data like books and articles and websites. Let me give you an example. Llama was a group of language models that were released in 2023 by Meta, and this is a data mixture of Meta used for pre training. So, Common Crawl and C4 are web scrapes of the internet that have been cleaned and filtered. GitHub data is programming code like Python or JavaScript. This is code that has been released under certain licenses like the Apache license, giving you the permission to reuse the code for nearly any purpose. And Wikipedia is the well known online encyclopedia. Books is a collection of open books. So this includes freely accessible to everyone like the Project Gutenberg Books Library. Archive are scientific articles and papers, and Stack Exchange is a network of websites with questions and answers across different topics. Now, a proportion of each of these datasets is sampled given by the different percentages when training on the data. So the epochs give you an idea of how many times the language model saw this data while training. For example, with the Common Crawl, the language model saw all of the sample data 1.1 times, it saw the C4 sample data 1.06 times, and so on. Now, you'll also need a lot of compute. This is processing capability in these massive server rooms where you have several hundreds to thousands of hardware accelerators and servers that you'll use for a couple of weeks or months that works through the training data. So these hardware accelerators are usually NVIDIA's GPUs or graphical processing units. These are like CPUs that you'll find in a computer. Their function is to run a lot of the language model training tasks in parallel. Now, a training run usually costs a couple of million US dollars, and what you'll end up with is something like OpenAI's original GPT-3 model called DaVinci. Let's take a look. So here I am in the OpenAI playground, and let's try and use this GPT-3 model as an assistant. Now, I'm going to write the prompt, write a shopping list. I have no idea what the output will be because it's probably seen thousands of sentences that start write a shopping list, and it could generate anything that's related. Now, what's really impressive is that you can see that after all the training the language model has gone through, it can generate English sentences that make sense. Unfortunately, it's not particularly helpful, right? What I was hoping for is that it would provide me a list of items, one on each line. Instead, what I've got is make sure you always use an app on the phone so you don't have to write down all of the information and so on. So let's see if I can try and trick the model into generating what I want by rephrasing my prompt. So here is a shopping list. And let me go ahead and use a colon at the end of that. And let's see what output we get. Now, this isn't much good either. So, what I've got generated from the model is current contracts with the following teams: Carnegie Hall and New York Philharmonic. The Pops appear at Carnegie Hall every season, and so on. Now, since this hasn't worked, let me go ahead and try and give the model an example of what I'm looking for. So, this is a shopping list of only fruit, and I'm going to list apples, oranges, and grapes. This is a shopping list of only vegetables, and I'm going to leave the large language model to complete the rest. And I'm hoping that it's going to give me a list of vegetables. So, let's see what output we get. And you can see that the large language model has been reasonably successful. It's only listed me one vegetable, it's a carrot, but it's then gone ahead and said this is a shopping list of only meat, and it's listed me with chicken. So the language model starts off well, but then it seems to lose the plot and it generates some other text. All right, so we've seen that the pre training step is a very compute heavy and expensive process, including a lot of hardware and data. And what we get at the end of this is a model that's good at generating and completing sentences, but it isn't great at following our instructions. So, if we want to be able to use language models as virtual assistants, we'll need something that follows our instructions. And so, we'll look at how to do this next. We've seen the problems with just a base large language model. It just doesn't follow our instructions to create a shopping list out of the box. So, how do we go about creating a large language model that will follow instructions we give it? In 2022, the OpenAI team released a paper called Training Language Models to Follow Instructions with Human Feedback, which is still the industry standard. There are two components to this training: supervised fine tuning and RLHF, or reinforcement learning from human feedback. Let's head over to the paper and take a look at the supervised training in the diagram on the left. The OpenAI research team would create a prompt, for example, explain the moon landing to a 6-year-old, and then a labeler, so that's a person who's skilled with working with text data, would then write out what the model should produce as output. So, for example, they may include details like it took place in 1969, the spaceship used was Apollo 11, and two American astronauts, Neil Armstrong and Buzz Aldrin, became the first human beings to walk on the moon. They would typically have tens of thousands of such questions, and after this, researchers will typically fine tune a model. Now, what they mean by fine tuning is that they would pass both the prompt and the expected output from the labeler for each prompt to the large language model and train it. This means after some training for a given prompt, the large language model gets better at producing output that resembles what a labeler would have written. So that's what's known as the supervised training part. So let's move on to RLHF. Let's say there's another task. For example, summarize the following news article. Now, let's say the news article is about research on parrots and the sounds they make. They would get this fine tuned model to generate 5 different summary outputs of the news article. The labelers would then rate each of the 5 summaries, rating them between 1 and 7 using an interface like this. Often, researchers also want to make sure that the models follow instructions and do not generate toxic content or fabricate information. So the labelers had to give yes, no answers to questions that address this over on the right. The labelers also answered questions like, did this model fail to follow the task? And did the output contain inappropriate content? And so on. And they ended up with a ranking of the 5 different summary articles that looked something like this. This is the labeling interface where the bottom 3 boxes are the summary of news articles on parrots that they've already ranked, and the top 2 are the ones that the labeler will work on next. We're now in the middle at step 2. So, this ranking of the articles is used to train another model called the reward model. Now, the reward model takes this input, the rankings from the 5 or so text generations from the model, and returns a number. Now, this number represents the labeler's preference. This reward model could be fine tuned to take an input rank text and output a number that indicates how well the labelers perceived it. The final step over on the right was to use reinforcement learning to optimize the original language model using the reward model. So, if the model generates the text that follows the task intent and is not untruthful or toxic, it's rewarded. And that's the crux of reinforcement learning. This way, a model is encouraged to generate text that would receive positive human feedback. PPO, or proximal policy optimization, is the algorithm used to calculate the loss, which is used to update the original language model. So let's take our earlier example of a shopping list and see the difference with a model that has been trained with supervised fine tuning and RLHF. And so I could use Text DaVinci 3 as an example. And let me go ahead and remove all of the prompts and say, write a shopping list. And let's see the output that we get. And this is excellent. This is exactly what we would want. We've got bread, milk, eggs, cheese, ground beef, cereal, and so on. All right, so we've looked at what supervised fine tuning and RLHF does. This combination of fine tuning and reinforcement learning from human feedback has produced large language models that are much better at following instructions. Go ahead and head over to the OpenAI playground and try and give a model a couple of tasks and see how it does.